Record. Okay, saturation. So let's say you have a signal, and then you take a look at it. But if you're only able to measure at maximum this, then the signal get over it, but you don't see it. So you will get saturation. Okay, so that is basically that. It's like when your eye look at the sun, the photoreceptor saturate. So then you look everywhere and you see saturation. Okay, so it's the same thing with any device. They do have a maximum that they are able to collect, and so with the camera you get sometimes saturation, and you will try to avoid that, because if you want to measure, and let's say if you want to see the curve here, then if you only get that, you don't know if there's something that moves like this, like crazy, or if it just smooth or anything. You can just figure out that it does that, but you don't. Okay? Most of the time you will deal, while you look at an image, you want to say, yes, this is my background, this is my object, and you will get the concept of thresholding. Okay? So the threshold is really at which point you say that this is an object and this is my background, from something that has value which varies in terms of gray. Okay? So here you set your threshold at that value, and then you get either black or white, and every white pixel that touch each other will be an object. And this is how you can count things or do many things from there. But the concept of thresholding is really important. You're going to play with it most of the time with many different data. You will need to identify this threshold, and this is the goal of your experiment, to be able to define that threshold and distinguish things. We are now talking really about an optical microscope, and the most important part of a microscope are, well, nowadays it's not really more important, but it is still, I think, really nice to have the ocular, so the place where you put your eye, which is nowadays sometimes a computer screen, instead of having those things where you look. But the computer screen will not be as detailed as the ocular, because you get the screen and the pixels, and there's also a transfer of the real data into an image. So there is a camera system between those things. So ocular is still a nice thing to add into a microscope. The objective and the condenser. So the thing that shoot light over your specimen. The objective is the collector, and the ocular is the part you use. And you need a light source, and there is many different ways to light your specimen. Well, many different ways, yes. Two main ways to light your specimen. So the transmitted light, so that you have a light source let's say below if you look here, but sometimes you get an inverted microscope and then the transmitted light is on top, the objective is on the bottom, and then it goes there and you have the ocular. That would be an inverted microscope, but here it's an upright microscope where the objective face down onto your specimen and the light source is under. And why it's transmitted, the light goes through your specimen, and what you observe is just the shadow that is produced by your specimen. So the object will be black and the background will be white. While when you use the reflection mode, the objective will be also your condenser, because that's what will condense the light onto your specimen. And the same objective will be the collector. And you're going to get a filter which will distinguish between the incident light and the reflected light. And reflection mode is taken also for fluorescence. So you will shoot a certain wavelength onto your specimen. Your specimen is going to absorb the light and re-emit another wavelength, which will be filtered by this glass, which is called a dichroic, because it divided chromatic wave. The chromatic is the color. So dichroic splits it in two. The ocular. Usually oculars give also a certain magnification, and most of the time it's 10x that it magnifies your image. So just using the ocular will make your object 10 times bigger. The objective, there are many things written onto an objective. And on most objectives, you will first see the magnification, which is usually in big numbers, and there's a little X beside it. Okay? And right after, you're going to find another number, which is the numerical aperture. So you remember that I did say that it was really important to remember at least the numerical aperture is a number which will give you the precision of what you can get as an image. So the higher is this number, the more resolution you can have. And this number will also tell you if you need an immersion medium or not. At least, well, give a certain indication, okay? Because numerical aperture is actually, yeah, that's the definition here. Numerical aperture is the index of refraction of the medium which is between your specimen and the objective. So the medium here, it can be air, it can be water, it can be oil. It can be also glycerol, it's rare, but it happens. So most of the time it will be air. And if it is air, the index of refraction of air is, you know, about close to 1. Yeah, it's really close to 1 with, I think, the number 8 that's somewhere in the decimal really far. So 1. And the sinus of an angle is a number which is always smaller than or equal to sinus of any number. It's always between -1 and +1. Okay? So it's always between the sinus. Yeah. So the sinus of any number will never give greater than 1. Never. It's either, well, in this case, it's going to be 0 or 1, in between, depending on the angle. If the angle is 90 degrees, then it's 1. Then if the angle gets around half, it's going to be square root of 2, and so on, okay? So it's either, if it's 90 degrees, then it means that the angle here is really, really wide, and it cannot be 90 degrees. It would mean that you have an infinite surface, okay? So the angle is usually really, really big, but at some point it gets smaller, and so that is the sinus of the angle. So a number which will varies. If it's 0, then it's 0. It means you don't have any length. But if the angle is small, so air, which is 1, times the sinus, which is between 0 and 1, the numerical aperture of an objective in air will never be 1. It's going to be a number below that. Okay? So if you see a number here which is greater than 1, then you know that it's an objective that needs immersion medium, either oil or water. Okay? Usually water is going to be like 1.2 numerical aperture. It's going to be over 1, but below 1.33, which is the index of refraction of water. Okay? So that is the other important thing. And it's always written, and if it's not written, it's because it's an air objective. Okay? So if it's written, then it's oil or water that's going to be written, or D0. Okay? So every objective, you have at least those 3 things which will be written on the objective. So if you face an objective, then you can at least look what's written on it in order to know what kind of medium to use, or just have some indication. Okay? You're going to have usually the specialized optical techniques that you can use of contrast written on it. There's always a color code also. So if you see a yellow strip, you would know it's a 10x objective. Yellow is 10. Red, it would be 5x or 4x sometimes. So low magnification objective will have a red strip. Blue is for 40 and 60. And black would be 100x usually. Okay? And you would also see another, sometimes white strip. White strip would be for dry objective. And black strip would be for oil objective. So you always have 2 color strips. One is, the top one is for the magnification, and the one which is closer to the lens surface is usually the immersion medium. Okay? So that's basically what you can get onto an objective. And also, high magnification objective, since they go really close to your specimen, they usually get the spring so that the lens can enter inside. So that if you move the focus too high, the lens is going to enter into itself. Okay? And don't break your specimen. Okay? Because when you get so close, if you go really hard, then it's going to crack your slide. So, but still be really gentle with high magnification objective. Don't go too fast or use the coarse focus. So again, numerical aperture, the angle of the cone that captures light. So you see with the high numerical aperture, the red cone, you get all those that are more than with, let's say, a blue cone, which would have this aperture on it. The other thing is the depth of field. So when you get a really high numerical aperture, you get a really thin depth of field. Okay? And so this goes also with the size of the diameter. So let's say you look at a certain thing let's say you have your object which should be here, and the focus is really here. But let's say your object emits some light from there. Then with this high numerical aperture here, rays are gonna, it will look really fuzzy. While with this aperture, it will still be kind of in focus. Okay? Because the depth of focus is the range in which things look at the right focus. Okay. This concept is going to be easier with the microscope itself. We will play around with it, and I'm going to explain in more details depth of field and numerical aperture. So again, numerical aperture, we saw its definition. So the index of refraction of the medium, which is between the slide and the objective, times the sinus of the angle. Condenser, yeah, and also depth of focus. Yeah. So let's say you only have straight rays that go onto your object. So if it's really straight, the object is going to block light, and then you're going to only have the shadow like this. But let's say your rays, if they do have a certain angle, you see that the light is going to be blocked by those straight rays, but if the rays arise from the side, then it will not really block all the light. Okay? And this is where you get details, having a really high numerical aperture, or really high contrast if you reduce this aperture. It will block light, and that's it. This is not so important, so it's just part of the slide that I will send you in PDF. Aberration. Those things are enough important, and this is another reason also why when you have a digital camera, you can play around with lens and make different magnification by turning sliding lens, and then you see in more detail something, and so on. And if you get a really nice picture, at some point you might see some aberration. If you play with a high zoom and you get not the really good quality of lens or things like that, you're going to see some, oh, maybe at the edge there are going to be some color which looks strange. And this is why when you have an objective in microscopy, it has a fixed focal, and so the conception of this lens is made of glass, which at this particular position, it will limit the aberration. So they made this lens to limit the aberration of chromatic and spherical aberration. Spherical aberration arises from the fact that at the edge of the lens, it will not focus exactly at the same position than from the center. Okay? So this is really spherical aberration. It comes from the fact that the light cannot really focus at the same position if it enters at a specific position from the center of the lens. Okay? And the other aberration comes from the fact that the blue, the red, and the green, the principal, the major component that your eye see, will not focus at the same position. And you remember the arc-en-ciel, the rainbow. So the refraction is not the same regarding the wavelength. And so there are ways to use some kind of class and put it at this position and this position and so on to correct those chromatic aberration. But this is why 10x objective will always be only 10x. And you cannot play with the lens and arrange it in a different way in order to get, let's say, 5x or something like that, because you're going to get too much aberration of chromatical or spherical aberration in order to get as detailed as you need from a 10x objective or 100x. Okay, now we are going to talk about the contrast method. There's the basic illumination, which is called the Kohler illumination. I think it's German, not sure. Phase contrast, so you always hear that, oh, I'm going to look myself in phase contrast. Yeah. And sometimes they do not even use phase contrast, but they still say that they use phase contrast. But I'm going to show you what you need to produce a phase contrast image. There's the Hoffman, which is not really well done, but it's useful and you can get a certain interesting contrast. Polarization that use polarized light, and I'm going to show you this. DIC, which is the letters are for differential interference contrast, and it's also known as Lomarsky, which is the guy who did invent the DIC method, and the fluorescence, which is used most of the time. So this is the widely used method, I would say, and those other methods are not really used, but still they are used, and they are basically used for transmitted light, while this one is mostly for reflection. And this is the easiest one, and those ones are really more difficult to achieve. This is mainly because of it that it's widely used, I guess, because it's so easy. And it produces a really, really nice contrast, and it's impressive, it's good looking, and so on. Kohler illumination. So it's just a way to bring the light onto your specimen and focus it at a certain position and make sure that it focuses at the same position than where your objective focus. Okay? So here it won't be adjusted the right way, because here you see that light is focused here while the specimen is there. This would be a nice adjustment, because this is where your specimen is positioned, so the objective would see at this focus range, and then you would focus the light at the same position. And there's a trick to align this at the right position, and you use the field diaphragm. Yeah, it's here. You use the field diaphragm in order, and that's why they call it field diaphragm, because it's in the same plane than your object. So once you focus your field diaphragm into your object plane, then you know that you are in Kohler illumination position. Hoffman used a slit pattern, and so that the light intensity, so the light is totally, will pass through here, and there's some window which has some pattern into it, and let's say here it would block the light, so the illumination is more from one side than the other. Okay, and you can all of you took the plane once? No? Yeah. Okay, at least to come in. Yeah. Okay. So when you're in the plane and you look at the ground. Yeah, did you have the chance to look through a window and see the earth and see the sun? And the sun is not always from top, and sometimes it goes really close to the earth. And then the lightning is really from the side. And then if you look carefully on the ground, you will see shadows everywhere in one direction. And the other position will be really bright. And it looks really like from a plane. When you look into a microscope, you look at your specimen, it's really like if you were really from top and you see the ground. And it's the same thing. And so when you bring your light source from the side, you're going to see some shadows that are created from your specimen, from the relief of your specimen, and you're going to see shadows on one side, and the other side is going to be really bright. And it's the same thing that you use. And yeah, that's it. So it looks really like if you have a big height and you look from really high when you look into a microscope. Polarization is another principle. So you use the fact that you use polarizer in order to bring some light which would be polarized onto your specimen. And some component of light are birefringent. And birefringent is a property of some molecules to have a different index of refraction depending on in which direction light go through the specimen. Okay? So if it goes in that direction, light is going to go really, really fast, and if it goes into that direction, light is going to go really slow. So the way light travels into the specimen is not the same speed. Okay? And those birefringent, do I have it? No. Oh, sorry. I thought I would have the. There's calcite. It's called. It's a crystal that has really organized way. Usually you see birefringence in crystals. So some structure. So the way the atoms are organized in space, light's going to go really fast in one direction and not in the other direction. And if you look through a calcite specimen, crystal, you're going to see two images. Okay? Let's say you have a pen, and I thought I would add it into the presentation, but let's say you have a pen and you use a crystal which is calcite. You look at it and you're going to see two pens into the crystal because some of the light goes in one refraction and the other part will go into the other. Yeah. So the light turns when it travels into birefringent materials, and you use that fact. So you use a polarizer that blocks the light 90 degrees from the other one. So you have one polarizer that polarizes the light into that direction, and the other polarizer will block the light that goes into that direction. So if you enter with light that goes into that direction, and you have a polarizer into the other direction, you're going to block all the light. Okay? Except if you have a specimen that is birefringent, light is going to go like this. Oh, it enters into that specimen, it's going to go into another direction, and when it hit the other polarizer, it will go through, and then you're going to see some light. Okay? So that's how it works, this technique. So you use polarized light in one direction, and you expect to see your specimen where it may turn the polarization, so that you see where is your specimen. And this will give, this is, when you look at biological thing, most of the time it's going to be collagen. Collagen is birefringent. So everywhere you see collagen, like here, you're going to see light that go through. And so everywhere here there is almost no collagen, and everywhere else where it's like orange, you have a lot of collagen, and then you know that you have collagen in your specimen. Okay? So most of the time it's going to be collagen, and elastin also will make light turn. Yeah. Phase contrast. Phase contrast. So everything that has a different refractive index. So light is not going to go at the same speed into a different refractive index. So just if there is a different refractive index into your specimen, it's going to make phase retards or advance, and then it's going to produce interference if you find a way to make your light interfere. And this is how it works. So basically what you do, you use a ring, actually a kind of an aperture that has only a ring slit that allow the light to go through. Okay, so you block the light everywhere else, in the center and on the edge, and so light goes into a cone. Okay, but a cone which would be filled only with light, and here it's totally black. So you have light that go like this and is focused onto your specimen. If you don't have any specimen, the light will go like this, shoot, shoot, and here also, pop, pop. It will never go into that zone because you have light that is focused, that go through the string, go there, there, there. If it starts from here, it's going to go there, enter here, go out, and come up. Never you're going to get something here, except if you put the specimen there that kind of diffract the light, then you're going to have something in the middle. So what you use an objective in which you grind something that will retard light with a certain amount of time just because of refraction index. So usually objectives they are made into a way that retards the light from half wavelength of green light. Okay, and they select green because that's the most effective contrasted wavelength for your eyes. And you cannot select all the wavelengths, so they select a specific wavelength, which is green. And so when you use phase contrast, usually you put a green filter in order to only use the light from green component. Okay? So if you really make the real phase contrast, you would use a green filter, and you would use that ring, and you would use an objective which has a conjugate ring grooved into its lens. Okay, so this is how you can really achieve phase contrast. If you don't have that, we're not talking about phase contrast, we're talking about other contrast method in bright field. I don't know which one, but it's not phase if you don't have a ring like that, and the specific objective which has the same size that fits this ring, then it's really phase contrast. The green is not really so important. It will work also with white light.
So,
Yeah. Yeah.
What's the advantage of using phase contrast over fluorescence, for example?
Over fluorescence, you don't need the fluorescent probe when you use phase contrast. So when you use phase contrast, you don't need anything to put into your specimen. So that's the biggest advantage. And it's also widely used because when you look cell culture into a Petri plate, if you look at it in bright field, you're not going to see anything because cells are really translucent. You will notice anything into your Petri dish if it's like, even if you have a really nice magnification, you might see some shadow of something that you can figure out it's a cell, but it's going to be difficult. You can achieve a pretty nice contrast by just closing the aperture of the condenser. So just to get light enter really straight. Okay, and this would be a way. So you would only have a beam of light which is really a cylinder and not a cone. Then you would get a good contrast, but you won't see that much detail. And if there's any dust here, you will see it also. So that way to contrasting is not really good because you're going to see something else than what you have in focus. So that's why you would use phase contrast. Phase contrast will give you pretty good resolution. You won't see any dust which are located somewhere else below or up to your specimen.
The condenser, right?
The condenser, yeah. So you need a ring into the condenser system, like this, and you need an objective. And usually with the objective, you remember I said here, it's written the contrast method. Usually it's going to be written pH 1, pH 2, or pH 3. 1, 2, and 3, it's about the size of the ring. A smaller ring will be pH 1, pH 2 is going to be a bigger ring, and pH 3 is going to be a much bigger ring again. And this is only because some objectives are already high numerical aperture or low and really low numerical aperture. So pH 1, you're going to see it mostly with 10x objective. 5, if you do have pH phase objective 5, it's rare. It starts about 10. And really high, so let's say a 63 magnification objective would be with the pH 3. But it's also rare. So usually it's pH 2, pH 1 with 10 and 20x objective. Because phase contrast is not going to be good at a high magnification range, because phase contrast make details a bit fuzzier. So it's not a really sharp technique. While DIC is a really sharp technique, even at high magnification. So if you want to see details in bright field, so without any fluorescent stain, then you would use DIC. So that's another contrast method where you don't need any fluorescent probe, you don't need anything, you just need your cells, your culture or your tissue, and then you can see it. This technique is more complicated, and why it's called Nomarski, because of those prisms here. The first guy who invented the prism is Laston, and Nomarski made it in a way to use it through the optical system. So basically how it works, those prisms will, so you remember I said if you look through calcite, you will see two images of one thing, because it kind of split light into two different paths. So that guy, Nomarski, figured out that he could split light into really, really small, different range of path, light path. Okay. So this is what he does. And the difference of path is smaller than the resolution of the objective. So light goes in a really, really small different path, okay? And the thing is that when it splits light into two different paths, light is not polarized in the same direction, okay? So let's say you have one direction of polarization. When it exits the prism, it's split into two directions of polarization. And light which is not polarized in the same direction can never interfere. If you want to make interference between one beam of light and the other beam of light, it needs to be in the same polarized orientation. So that's really nice. So polarized beams are not interfering at all. And then he uses another prism, which is the same thing than this, but instead of making them apart, it brings it at the same position. So now they are really positioned at the same place, and then he uses another polarizer, which is called an analyzer, because it takes only one part of polarization and use the two components which are in the same polarization and make them interfere, and this is how the contrast is generated. It's just generated by interference. And it gives something like that. So you see the kind of shadow behind, which is the differential interference contrast. And on top of it, we have a stain. So here you see the stain, and you can distinguish also the shape of, I think this is one cell, this is another cell, this is another one. I'm not sure about the image. But yeah, but you still see your stain, and you can figure out what looks like your specimen surrounding it. Dark field, that's a funny technique. Dark field is similar to phase contrast. You don't need a ring to make the light interfere, and actually you need a ring which has a bigger aperture than your objective. So what you do, you take light, you shine it onto your specimen, and let's say light goes like this, and your objective is here. If you don't have any specimen, the light is going to go like this and will never enter into your objective. It goes outside of the objective. It's like if I get a really big flashlight and I'm out of the room here, and the flashlight is somewhere in the corridor, and I don't see the flashlight, I can still see some light. And the light that I'm going to see is because of reflection or refraction from the walls and things like that. So it's the same principle here. You shine a light onto your specimen that if there is no specimen, it will never enter your objective. And so that's what gives rise to those kind of contrasts.
But that would make it harder to decrease the noise in the slide, for example.
Actually, no, because the only thing that you will see is really small things. So it's only small things that will make the light change direction enough to enter the objective. So usually, like here in this specimen, there was a staining with, I think, silver particles. And so those silver particles are really, really small. You cannot even see it in the specimen here. But if you use dark field contrast, then you see all the particles which are located there, which is your marker, actually. So you use this kind of contrast. So dark field is really used into a really special case, I would say. But if you have a really, really fine things, so I've used also dark field with neurons. Sometimes you have a neuron that is really, really small, and it's hard to distinguish it from the background. And when you put it in dark field, poof, it's like a flash. Then you see only the neurons. And, yeah. So it's a nice technique also. So it's used in specific case, I would say. And now we're with the fluorescence. So basically you have what's called an excitation filter, and you have an emission filter. And in between you have the dichroic. And if you look at the transmittance graph, so transmitted is how percent it transmits light. So if you have a specific filter for, let's say, excitation, so it would be here. So this one would transmit light only in this portion. So this blue guy would only transmit light in this portion. The dichroic will not transmit light below a certain wavelength and will transmit light from the other wavelength. So that if it occurs like here, poof, the blue arrives here, it does not transmit light at all. So if it's not transmitted, it's going to be reflected. It's going to go down. Your specimen, oops, so like this. So blue light, shoot. Okay. No. Okay, like this. Blue light, blue. Then your specimen absorbs the blue light, takes the green and read it. And so green will go through this glass, and then you're going to see only the green. Okay? So let's play it again. Blue, excite, fluoresce, poof, goes back. That's how you distinguish the grain from your GFP. And it gives that kind of image. And here you see the blue nucleus, the green fibers, and the red, which appears in kind of yellow here because the green and the red are superimposed in the same position. But using different probes, you can distinguish different structure, and this is mostly what you will do with fluorescent techniques. Yeah, I think we are almost ready for the second pose. It's gonna be here. Yeah. Okay, so 2 more slides. But I think I will stop here and just start the third part with the advanced techniques. That's good? So we take another 10 minutes.